or we're going to need some length of the data, and it's broken up into these different chunks. We load a large block of that data all at once into shared memory. We're going to end up loading some data that we never reference because we preserve the alignment of the bytes within these tiles, because then we can just subtract off the starting address from the global memory starting address. We subtract that off from these indices, and it becomes the address for the same data element when it's in shared memory. And that keeps the indexing arithmetic very simple then. If we didn't do that, then we would have all kinds of indexing calculations to figure out which element here mapped to that element there. By keeping them uniform, life is much simpler. And the only key thing to worry about then is we want all these things to be aligned on these coalescing boundaries so that when we do our global memory reads, they're all running at peak performance. And so the way that ends up looking in the code, this is one of those loops. So you saw the constant memory version just read from constant memory. Because we don't know if the data is in the shared memory or not, right before we go into this loop, the last thing we do is we have to sort of determine, given the starting index of the first thing that we'll reference, and the run length of how long it's going to zip through that array, we basically have to do a little math, check to see if we've got that data that it's going to need. If we don't have that data, then we basically load several of those tiles into shared memory right before we go into that loop. And by doing that, a big load all at once, we then don't have to do any tests inside that loop. We can guarantee that once we've loaded it, we have everything we will ever need within this loop. So this is basically a single test and a single load operation, and we avoid having that in every loop cycle. So that makes it much faster. Any questions on that? And so with Fermi, we have all kinds of new opportunities. We have a much larger shared memory. We have L1 caches on global memory. And so we can run multiple kernels concurrently, all kinds of other good stuff. And of course, the machine is much faster. One of the things that's really nice then about Fermi is we can basically write the code in a much simpler way and get the same performance that we did for the best performing version for the older GPUs. So instead of having, you see these arrays no longer have that, they're no longer prepended with const or shared. We are literally just pulling data straight out of global memory, but because we have the L1 cache and because we have our memory references organized in that perfectly consecutive access pattern, we get basically the same performance for a much simpler kernel that we got for the very fast and most complicated kernels. And this one works for all problem sizes. So there won't be any problem size that this kernel can't do. The only thing that will happen is as the problem size gets bigger and bigger and bigger, at some point it will get to be so big that it might not fit entirely in cache, and so the performance will begin to degrade. But at that point where that's happening to the Fermi kernel, the other kernels would be unable to, they couldn't even run. They would have exceeded their hard-coded capacities. They are unable to run anything that goes beyond fixed size. Now, granted, we did a lot of sort of research to figure out, well, what's the largest angular momenta we would ever have to handle. You know, we went and we looked up in the basis set library that's on the web, what's the craziest basis set anybody has. And we figured out how to size our shared memory so that in principle, at least, in no time in the next few years would we run out of shared memory in the existing kernels. But let's say that this code outlives our plan, you know, and people in the quantum chemistry community come up with really wild basis sets. This code will work, period. It cannot fail. It may get slower, but it cannot fail. So that's one nice thing about Fermi. It's much easier code to read and write, and the performance behavior of caches tends to be pretty good if you have that good access pattern, even once it gets big. And so you've seen, basically, we have this small 64K memory on the chip, and it's either divided into 16K of shared memory and 48K of cache, or 16K of cache and 48K of shared memory. It's up to the programmer which way you want to set it. We actually tested our orbital kernels with the the Fermi L1 cache set to the 16K size, and even with the small 16K size, you can see it is very nearly, it's only 1/100th of a second slower than the fastest constant cache kernel. That's not bad at all. And so that's very encouraging for us. And so that's a speed up of 117 versus the fastest Xeon machines we happen to have in our lab. So then the last thing I wanted to cover is basically dynamically generating kernels. So I described one of the performance issues we have here is that if you look at these loop counts, when we're dealing with short loops that only have a few iterations, we're getting a lot of what I would view as being unnecessary overhead from the loop construct. And if it's a short enough loop, then it becomes very reasonable to consider fully expanding that so that there is no loop and it's just a straight sequence of code. If we have a loop of hundreds of items, that becomes unreasonable because feeding that to a compiler becomes thousands and thousands and thousands of lines of code or millions of lines of code. But if we have a short loop, that's very reasonable. And as I demonstrated for the angular momenta loop, expanding those into complete code sequences was a big performance win. That was probably a factor of 3 performance win just to do it here. So doing it here in our testing gives us 40 to 70% speed boost. And what's nice then is, so with both CUDA and OpenCL, there are ways of compiling kernels on the fly. In CUDA, you would do this at the present time. They don't have a way to do it from the C-level CUDA kernels, so you do it with PTX. With OpenCL, by its very nature, you always compile the kernel at runtime, and you're always giving it C-level source to compile from. And so both of these are pretty easy to deal with, but the C-level source is probably the easier. The only difference from what we did before is we would add basically a new step here. After we've read in the QM simulation log file and we've pre-processed all the data, then we walk through that data once, basically walking through it in much the same way we would here, but rather than computing anything, we are basically reading those basis set coefficients and we're going to emit code instead. And once we've got that code, we compile it, and that will then live for the lifetime of that loaded simulation molecule. So that becomes associated with that molecule. The kernel is associated with it just like the atom coordinates are. And if we delete that molecule, then we would delete that kernel as well. And so what happens is this short loop sequence here becomes, instead of this loop, it becomes 3 lines of very short code, and there's no loop overhead whatsoever. So we go from something like this, which contains branches and a bunch of array lookups, and we replace all those array lookups with constants, which is a beautiful thing. So that means that those orbital coefficients are actually now built into the code itself. We're not even fetching them from an array anymore. We get rid of the memory reference. It's actually encoded into the machine instruction, or at least the compiler has the opportunity to basically bake that number straight into the machine instruction. And so that becomes what they call an immediate mode constant. And so now we have 3 lines of code, a smaller number of floating point operations and indexing instructions. So that gives us, going from this code with all this setup and indexing arithmetic to this, and that gives us on the older machines, older GPUs, about a 40% speed boost. On Fermi, this is a 70% speed boost. So that's pretty wild. And that's all it is. And you can see that, of course, expanding all these loops, the code becomes much longer. But as long as we know those loops are within a reasonable threshold, that's a good exchange. And we can always change our code generator to determine, well, if there are 100 loops, maybe we shouldn't fully expand that code because it'll balloon into a million lines of code and it'll take 5 minutes to compile. So that, there are trade-offs. How much time do you spend waiting when you first load the simulation log file for that kernel